Attacking Unix Systems via CUPS Part 1, Overview and Analysis. In this section, we'll explore how attackers can exploit Unix systems through the Common Unix Printing System, or CUPS. CUPS is a modular printing system that allows computers to act as print servers. It's widely used across various Unix-like operating systems, including many Linux distributions, BSDs, and even potentially Chrome OS and Solaris. We will analyze the vulnerabilities within CUPS and how they can be leveraged for attacks. Understanding these entry points and the potential impact of an exploit is essential for developing effective defensive strategies. This knowledge is particularly important because CUPS runs with elevated privileges, making any vulnerability a potential risk for remote code execution and unauthorized printer installations. In this summary slide, we'll recap the main points from our previous discussion on attacking Unix systems via CUPS. The impact of these vulnerabilities includes the potential for remote code execution, RCE, and unauthorized printer installations, posing significant security risks. The entry points are primarily through UDP port 631, which can be accessed from any source, making it a highly vulnerable target. Most GNU Linux distributions are affected, as well as some BSD variants, and possibly Chrome OS and Solaris. To mitigate these risks, it's essential to disable and remove the CUPS browsed service. Additionally, ensure that the CUPS package is updated to the latest version to address these vulnerabilities effectively. In this module, we'll walk through the discovery of unusual network behavior related to UDP port 631 on a new laptop. During the configuration process, Netstat ANU was utilized and highlighted an anomaly where CUPS, which typically operates over TCP, was seen using UDP. A closer investigation using the Lsof 631 command revealed that the CUPS browsed process was active on UDP. This finding pointed to a potential security issue that could affect various systems, including most GNU Linux distributions, some BSDs, and possibly Chrome OS and Solaris. Therefore, understanding and addressing this behavior is essential for maintaining network security. Now, let's talk about CUPS browsed. CUPS browsed is a component of the CUPS system, and it's responsible for the automatic discovery and addition of printers on your network. This tool makes printer setup seamless and unattended, meaning users can set up printers without manual configuration. However, due to its default settings, CUPS browsed can be exploited. By allowing connections from any IP, it opens up a vector for potential security risks. On this slide, we'll discuss the discovery of a vulnerability related to CUPS browsed. Using the Netstat command, we identified that CUPS browsed was listening on UDP port 631 across all network interfaces. This discovery was made through the command netstat anu grep 631, which was able to reveal that CUPS browsed had an open UDP socket on this port. To illustrate, when running netstat anu, the output showed entries like UDP 0.0.0.0 631 0.0.0 asci. This indicates that the CUPS browse service is accessible from any IP address, making it a potential security risk, especially in its default configuration. This finding was a critical step in understanding the exposure of this component and the necessity for further security measures. In the previous section, we examined how the Netstat utility can be used to reveal open network ports and identify services running on those ports. We noticed that CUPS browsed was listening on UDP port 631 on all interfaces. To further investigate, we employ tools like Lsof and PSOX. The Lsof command helps us identify which processes are associated with specific network ports. For instance, using Lsof-I 631, we can see exactly which process is using port 631. Additionally, the PSOX command can confirm that CUPS browsed is indeed running as the root user. Running PSOX grep CUPS brow shows the detailed process information. These investigative steps are valuable for understanding the processes and services on your system, setting the groundwork for identifying potential security issues and misconfigurations that need to be addressed. In this section, we are examining issues related to stack buffer overflows and race conditions within the CUPS browse service. Our investigation revealed that there was no fuzzing coverage for CUPS browsed, a gap that exposes it to potential vulnerabilities. Specifically, several parsers within the code lacked proper boundary checks, which are critical for preventing buffer overflows. To address this, we utilized American Fuzzy Lop, AFL, to uncover parsing issues. Here's an example target function setup. cgot equals receive from browses socket packet size of packet nice 1 0 and sarcadr.adr and srclen. This function call receives data into a packet with the size limited to prevent overflow. However, without adequate checks, it remains a point of vulnerability. Understanding these vulnerabilities is essential for securing your services and ensuring robust boundary checks are implemented. In this section, we'll discuss the found_cups printer function. This function's primary role is to discover a printer by validating and parsing URLs. This is a critical part of the process as it ensures that the URLs are properly formatted and valid before further processing. Here's a simplified example of the function. cint found_cups printer, const char remost, const char URI, http separate URI, http URI coding all, URI, scheme, processing and validation. In this snippet, the http separate URI function is used to dissect the URI into its components. This is an initial step in handling the URI, followed by further processing and validation steps within the function. Proper validation here is essential to prevent any potential security issues or mishandling of the data. This function exemplifies the meticulous care needed in handling external data, ensuring that all inputs are correctly separated, validated, and sanitized. Let's now focus on leveraging IPP, or Internet Printing Protocol. IPP is a robust protocol applied for communication between client devices and printers using HTTP POST requests. This allows us to query various printer attributes effectively. Take this example of an IPP server response. Here we receive printer details such as printer info and printer make and model. In this sample, the server responds with information indicating my printer and Evil Print Co. Model X. This information can be utilized in managing printer configurations, troubleshooting, or even automating administrative tasks. By understanding how IPP works and how to interpret these responses, you can significantly improve the efficiency and accuracy of printer management within your network. PostScript Printer Description, PPD files, are critical in defining a printer's capabilities and command operations. These files include various attributes and parameters that instruct the printer on its functionality. However, there's a significant vulnerability when these PPD files handle unsanitized attributes. For instance, consider the example shown, Foomatic-rip command line, on, ta. This line within a PPD file illustrates how unsanitized attributes can be exploited, leading to potential command execution on the system. This vulnerability can provide attackers with a method to execute arbitrary commands, thereby compromising system security. Understanding and mitigating these vulnerabilities is essential in maintaining secure printing environments. Next, we'll explore how legacy components like Foomatic-rip have contributed to such security concerns historically. The slide at hand focuses on the problematic child, Foomatic-rip. Foomatic-rip is a legacy cups filter that allows command execution through PPD parameters. This issue has its roots in the historical context of past vulnerabilities, such as CVE 2011-2964, indicating a long history of exploitation involving this filter. Essentially, this slide highlights how Foomatic-rip has been a repeated target for security breaches due to its capacity to execute commands via unsanitized PPD attributes, making it a significant concern in the realm of secure printing environments. Let's explore how remote command execution can occur through a chain of vulnerabilities. This chain begins when a connection is established to a malicious IPP server. Once connected, specific PPD directives are injected. These directives dictate how the printer should process print jobs. When a print job is queued, the injected directives are executed, leading to command execution on the print server. This kind of vulnerability highlights the necessity of securing print server communications and validating PPD files to prevent unauthorized command execution. Here we have an example exploit configuration demonstrating how this chain of vulnerabilities can be practically applied. In the APEEP section, we specify the printer name as Evil Printer. This indicates the malicious printer setup we're working with. The printer privacy policy URI is pointing to a URL, which in this example is https://lww.google.cache. This might be used to trick users or bypass security measures. Pay special attention to the PPD directives here. The Foomatic-rip command line injects a command that writes the value 1 into the /tmp pwined file, effectively showcasing a benign but illustrative example of a command being executed. Lastly, the cupsfilter2 directive is configured to hijack print jobs, targeting specific MIME types to run our Foomatic-rip filter. This slide exemplifies how a seemingly innocent printer setup can be manipulated to execute arbitrary commands, highlighting the severity of potential security breaches. Personal considerations. Now let's look at some personal considerations from this research. First, discussing responsible disclosure challenges with developers is essential. It's not always a straightforward path, as coordinating with developers to notify them about vulnerabilities can be complex and time-consuming. Next, consider the impact assessment and the mitigation recommendations. Understanding how these vulnerabilities can affect the system and determining effective solutions are critical steps in improving security. Lastly, reflect on the CVSS scoring. It's an important metric, but remember that nuances in the scoring and the dynamics within the security community can influence perceptions and urgency. This understanding will help you better navigate the landscape of vulnerability management and mitigation strategies. In this slide, we summarize key points from our discussion on the vulnerability in cups browsed. It's critical to understand that this vulnerability can lead to system compromise. The exploit involves several stages, including an initial UDP packet, unsanitized IPP attributes, and ultimately, command injection. On the practical side, immediate action is crucial. Updating or disabling cups-related services is a primary step. Additionally, ensuring robust network isolation and applying stringent firewall policies will help mitigate the risk. These points encapsulate the essence of the vulnerability's impact and the primary mitigation strategies you should implement to protect your systems. For those looking to expand their knowledge and resources on this topic, here's a list of recommended tools and readings. First, tools like AFL, which is an automated fuzzing tool, can assist in vulnerability discovery by automating the testing process and identifying potential security flaws. Standard tools such as Lsof and Netstat are invaluable for network and process enumeration, providing insights into open files and network connections, respectively. As for articles and documentation, the official CUPS documentation should be your go-to source for understanding the intricacies of CUPS and its workings. Additionally, reviewing the RFCs on the Internet Printing Protocol (IPP) and Printer Description File (PPD) format will provide the technical depth needed for more advanced comprehension and troubleshooting. Now that we have covered the tools like AFL for automated fuzzing and standard network and process enumeration tools like Lsof and Netstat, it's time to discuss the next steps in our journey. To gain a deeper understanding, you should study the detailed PPD specifications and the IPP protocol. This knowledge will provide a solid foundation for more advanced topics. Additionally, exploring fuzzing techniques with AFL will help in discovering potential vulnerabilities automatically, making it a valuable skill in your toolkit. Lastly, applying network security best practices will minimize your exposure to vulnerabilities, enhancing the overall robustness of your systems.